Morning, guys. First session today. I'm Alex. I'm the guy behind Tezos. I don't know who of you already kind of uses block explorers in Tezos and who not. I'm running a company who does data mining on blockchains. So our core business is extracting information out of blockchains and making this information accessible to different types of use cases. These use cases could be kind of analytics, so you'd understand what's actually happening at a larger scale in a blockchain. That could be auditing, so where you look at certain accounts and are looking at what's going on certain accounts, how many transactions are going in and out. So this is basically the use cases we are concerned with. Brief agenda and brief goals. I want you to learn a couple of things today. The first thing I will go into is I like you to understand what an indexer does, and also when you should use an indexer and when you don't use an indexer. That's kind of the first goal. And the second goal is, I kind of assume that most of you will be implementing smart contracts going forward. And there is a couple of things that you should know when implementing your smart contracts to make them better indexable, so to say. And there's a couple of other things you maybe should avoid because that makes your contracts harder to index. Yeah? And this is what we will also kind of go through. Yeah, and since everything we do is open source, you could actually also run everything that I'm showing today also on your own laptop. You can crawl your own kind of private networks. You can also crawl the public networks in Tezos with our software on your laptop and run this totally locally. Yeah? You don't have to hit our APIs. You can be completely self-sustained with our software. And I just briefly in the end show you how you can do this. So let's jump right into why do you need indexing at all? So when we look at blockchains are kind of basically the lower part here. The idea of blockchains is to give you a sort of a new distributed database where you can store information and you can agree with different entities on the truthfulness of this information, on the validity of this information. And what a blockchain basically gives you is, or implements, and this is no different between all the blockchains that exist, and Tezos is no exception to this, is that on the lowest layer we have some sort of a system that manages a ledger, and the ledger contains usually a block archive, which is kind of the history of all the blocks and of all the transactions. And in these smart contract platforms, it also contains a thing that's called context or storage. That's basically the storage combined across all the different smart contracts. And also across all the different accounts that live in the system, because most of these blockchains, they also allow you to own coins and have addresses. And kind of this entire storage is represented, what Tezos calls a context, other blockchains just call it storage. So that's the lowest layer, and this ledger basically gives you the storage and the integrity of the storage. And it makes sure with a consensus algorithm, this is where different blockchains differ from each other, but there is a consensus that all the different nodes that basically replicate the same storage arrive at the same kind of state after an update. So this is what the consensus is for. It's basically nothing else than a distributed or replicated database with a consensus, worldwide consensus algorithm, where all the updates are ordered and every node arrives at the same state. That's the idea. So, but since we have a database, we also want to have a little bit of a functionality to that database. And this is where our smart contracts come in. Like in the old database world, you would do something like stored procedures. Yeah? Some code that runs inside the database server to work with the data that is stored in the database. In blockchains, we do this, we call this smart contracts. And that's basically some code that works on the storage, that takes some inputs, works with the storage, and produces some outputs. Nothing else. Yeah? And the results are stored back again in the storage. And then also it gets distributed with the consensus. since the system is mainly focused on achieving consensus and achieving integrity, the data models down here, they're not very optimal to build applications on top. Yeah? What you actually need to build a real application, like with a regular database, you need this as well. You need a query layer. You need to be able to express queries against the data so that you get certain information out. And this query layer in databases is usually kind of SQL implementation. And here in blockchain land, we need a database interface that also allows us to have certain indexes over data. So we want to understand which transactions belong to which accounts. For example, we want to understand what's the current balance of an account, or what's the balance 5 days ago. And all these different things, they happen inside an indexer. And this is kind of the thing we are talking about today, the indexing layer on top of blockchains. Yeah, and then finally you can build your applications on top. You could build your applications also right on top of the blockchain itself. Yeah? But at some point in time, you will need some sort of an index for yourself. You can build it yourself also, learn the concepts today, but you could use an index that exists. So in the different use cases, there are basically plenty. You can do an account reconciliation, like checking balances over time, or balances at the 1st of January for tax purposes maybe. You could do audits and compliance work. You could do analytics and research, and so on. So there's many different use cases for these indexers. And please feel free to stop me anytime and ask questions if you have questions for each of these slides. So let's jump right into the indexing side. Now this is the query layer on top of blockchains. What's the basic idea, or what's the purpose of an indexer? One of the purposes is to track accounts, meaning which roles an account is in. In Tezos, we have these different roles. We have a regular account, and then we have these different bakers who kind of secure the network. We have these delegators, also different role. So you want to understand at which point in time, which account owns which, or is in which role. And you want to understand the status. For bakers, for example, you want to understand if this baker is active, or if it's inactive, if it's producing blocks or not, or allowed to produce blocks. And you want to understand the history, like the balance history, for example. So how much did my account own in Tez last year in June? What you also want to track in an indexer, because this is nothing the blockchain gives you with a call, you want to track the total supply. And not only the total supply, so all the coins that exist, but also the different pockets of supply that sit or that are owned by bakers. The supply that is maybe frozen in Tezos for consensus purposes. So there's many different parts of the supply you want to track, and this is nothing the blockchain gives you out of the box. That's why you need some tracking mechanism on top. And on top, when you build smart contracts that own tokens, this is again also nothing the blockchain itself kind of gives you information about. You want to track your own supply, you want to track your events that are happening in your tokens. Whether you mint something, whether you burn tokens. These are all purposes that you need in the outside world when you do taxing, when you do accounting, and so on. So those are important events, and those are also things you want to put into a database. So that's basically the task of an indexer. So let's look at how an indexer works. So usually we rely on an archive node for indexing purposes. An archive node in Tezos is a node that stores all historic state. It requires more storage. And in this case, this archive node does not prune or delete old state from its context. It just keeps the state. And you can ask the archive node, what was the state of this account at block 1000, for example. So that's the idea of an archive node. Yeah? It always keeps all state. But this state, although it's there, it's not very efficient to get out of the node. It takes a long time. When you, for example, want to query all the accounts that existed at block 1000, it takes a couple of seconds to do this. And you basically want to have a faster way to do this. So what's happening is you usually build some sort of an extraction job. Yeah? ETL is kind of the term for extract, transform, and load, meaning you extract data from an API. In this case, it's the RPC API of a blockchain node. You extract it, then you transform it. In this specific case, the transformation happens because you, on the one side, from the blockchain, you have a complex JSON object that has nested sub-objects, and you transform this into a table structure, so you can store it in a database. Yeah, that's the idea. So you take this nested, complicated object, and you flatten it out into one or multiple database tables. And the load part of this job is actually the insertion into a database. Yeah? So this is what's usually happening. So you extract it, and then usually this is what most people do is they put it into a SQL database, not thinking very much about what will happen to this data later on, just to be generic for other use cases. Sometimes, like for supplies and so on, you need some sort of very heavy queries against the SQL database, which you don't want to do kind of in an online way. So you have offline queries, and you store the results back also in the SQL database. And in the end, yeah, you build an API layer on top, and this API layer gives you kind of the results you are asking for. So that's basically the structure. There are some troubles with this structure. This works for small blockchains, no doubt about this. But when the blockchain grows, say for example, when we take Bitcoin, you pay a lot of money. So you need different ways to do this. And or your queries are very slow. So the trouble is that first of all, the queries, when you query the Tezos node, they are quite expensive. So you shouldn't do this very often. Yeah? Then when you want to do analytical queries, so for example, you want to understand how much supply was moving over the last 3 months, doing this out of a SQL database is dead slow. These ETL jobs are often made in a way that they are simple to implement. So they just take the data that comes out of here and just simply map it to a flat table structure. That works for starters, but this never thinks about which type of queries you have on top. So the data that ends up in your SQL database might be not the most optimal data structure you have. And what people usually do is to throw in more speed, they generate indexes here, which kind of blows up the storage requirements of the SQL databases tremendously. But just to have more indexes, just to have faster queries. But without thinking about the other way around, like what type of queries we want to do, and maybe do the extraction in a better way. This is usually not what happens today. SQL databases are not very efficient when it comes to analytical data processing. Basically, it's about how they kind of lay out databases on storage, and they need to load too much data from storage when you only need to access certain amounts of columns. There is better data stores, like columnar data stores, and I know people who kind of really process large amounts of blockchain data for the big blockchains, or the blockchains that are very fast, that have kind of second block times, like 5 seconds or 15 seconds block time. They basically use columnar databases to do analytics, and they are much, much faster. So what we basically did with the TC Stats backend is we built a new generation of an indexing engine for that. And this new engine also uses a Tezos archive node, but this engine is based on a new type of data store. It is a columnar data store, so similar to what other people use, like ClickHouse, for example. But this data store is an embedded, so it's not an external database server. You don't need to operate an external database server or an external cluster of database servers. It's actually an embedded database that kind of sits next to the indexer. And this kind of close connection allows for much more efficient indexing of the blockchain. and much more efficient layout of the storage. So what we basically did is we looked at the type of queries that you want to run against such type of an indexer. And then we didn't do a bottom-up approach, but a top-down approach. So we looked at the queries, and then we looked at how could we efficiently support these queries in a database. And this takes away from the concept of normalization from databases, where you store one data item only once, and then you maybe link tables to each other by foreign key relations. But instead, because this data store is more efficient and it uses smart compression, we actually kind of duplicate data when we have the need to. We even duplicate data in terms of using Booleans, for example, as flags. So we can do faster searches and faster filtering over different fields. In the end, we don't need indexes in that database. We just basically use filter expressions over Boolean columns, over integer columns, and so on to quickly find data. And it turns out that for the very limited use case of blockchain indexing, this is kind of a highly efficient architecture.
What exactly storage do you use?
So the storage engine is a self-built storage engine. So it's a custom-made own engine.
Why, for example, not RocksDB or something like this?
So there is one reason. I looked into ClickHouse. I looked into other columnar data stores. So first thing, I wanted a columnar data store because I needed column vectors for fast analytical queries, but I also wanted column vectors for easy compression of integer data and other types of data. The normal columnar databases don't really support updates that nicely. So ClickHouse is very slow when you do updates, when you have reorganizations, or when you have tables, for example, an accounts table, where you track the balance, the most recent balance. And for this reason, because the update side is inefficient in most columnar data stores, but there is some nice features, I kind of merged both worlds. And it's basically a columnar data store with a journaling solution on top, where updates go into a journal and are written out into the columnar data store when the journal runs full, for example. And for Tezos and Bitcoin, it turns out to be kind of a good structure to do this. So the data storage requirements are very low. It's a third of the blockchain size. For Bitcoin, for example, it just needs 100 gigs of storage. When the blockchain is 300 gigs in size, but this includes all the statistics, all indexes across everything. I would still say this is an early development. It works for Tezos, works great. So all TC stats, it serves 3 million calls a day, or like the last days where the price went crazy, it served 5 million calls a day, come out of a single server. And this database is not even multi-threaded right now. So it's highly efficient. And there is still a lot of room for improvement. Eventually there will be a database server, but right now this is maybe only 6 months of engineering work went into this.
Good, thank you.
Yeah. Okay, let's jump into when you should use or when you need an indexer and when you should not use an indexer. Let's start with the when not. So an indexer is another moving part in an infrastructure. And because it's a separate part, it might introduce errors and bugs. No software is error-free. I mean, everybody in the room should know that. So for this reason, when you really need kind of ground truth data, when you need data that is kind of trusted, or when you need signatures for the data, you should always rely on the RPCs of the blockchain node, because you kind of don't have a separate moving part in the middle. I'm not saying there is no bugs and no errors in the node implementation or the RPC implementation, but you have less bugs and less errors. So like everybody who wants to do, for example, a payout solution for Tezos, for Baker payout, tracking and so on, we tell them don't use our indexer, just use the RPC, because this is much better. You have less errors there. Yeah, you need to trust less systems. specifically, the RPC is slow in a sense, but if you only have 10 queries a second, or if you are only monitoring 5 accounts, you would still want to use the blockchain node RPC and not an indexer. And maybe build your own index across your small accounts. Yeah. So those are things you want to look out for. You should or you can use an indexer when you need bulk access to large amounts of data. Like you want to data mine all accounts. You want to data mine all transactions that happened on a specific day. You want to filter different accounts by balances, or you want to filter transactions by certain criteria you are interested in. This is very slow when you would do it with the RPC. That's why you want to have some sort of an index on top that tells you, okay, this is the list of transactions, these hundreds of transactions, they were over an amount of 1 million tests over the last month, for example. Yeah. This is what you get out of an indexer. Specifically, you also need an indexing solution when you want to do analytics, yeah, or statistics. Like, for example, you want to track income, you want to track how well the different rights that are assigned to bakers have been utilized or not utilized, maybe lost and stolen and so on. And also what blockchain nodes usually don't support is kind of the export to different data formats. Yeah. When you want a CSV file, you don't get it from a database. From a blockchain node, you need a database for that. So, before we jump into the next section, which is going to be a deep dive on how indexing is done, maybe you want to build your own indexer. Quick question to you. Do you have any questions until that point? No questions? Good. Ready for a deep dive? Well, okay. So that's the reason why I asked before whether you know blockchains already a little bit, like Bitcoin and so on, because we look into not too technical, but a little bit technical details. Okay, so bear with me. So what we are interested in, so there's different angles to approach this. We could kind of do kind of thorough indexing, like every account, everything that's going on, or we can focus on smart contracts. I kind of decided, because you had this course before where you implement smart contracts, and I kind of guessed that most of you are interested in kind of building smart contracts and building applications on top. So I focus more on the side where you would want to understand and index the data around your smart contracts that you are building. So that's why let's look into what's going on around the smart contract specifically. So a smart contract is a piece of code that kind of lives on a blockchain, that is kind of stored there on a blockchain, and is executed by every node when a new transaction comes in for this contract. When a transaction kind of arrives, this transaction carries some input parameters. It's basically a function call you make to a remote node through a transaction that is signed and then executed across the world. So this transaction carries input parameters. They go into your smart contract, your function you want to call, and maybe also the function name or some sort of a signature or a pointer to the function. When the contract runs, it usually reads data out of storage in the node, does some computation, and writes data back to storage. And in the end, you could have a return argument or some sort of a receipt. Now, Tezos supports input parameters, but Tezos does not support return arguments. Yeah? So that's a very specific design decision that has been made in Tezos. That is different from Ethereum, for example, where you have explicit return arguments. Yeah? But all these functions, like input, output, read and write, they always exist on all the different blockchains. So when we look into how this is done across different blockchain systems, let's connect this. In Bitcoin, your input parameters are the spending script. Yeah, that's basically the script you publish at the point when you want to spend unspent outputs. Before that time, the spending script is unknown. It's not published. The only thing that's maybe published is a hash of the spending script. Yeah? And that's your input. The reads and writes, they don't really exist explicitly in Bitcoin because there is no smart contracts and no arbitrary storage. Basically, the only thing that's stored in Bitcoin is the outputs. And the outputs, they are called UTXOs, like unspent transaction outputs. And that's basically the two things you see when you look at a Bitcoin transaction. And when you dissect the binary, and when you see what's there, you have an input script, and you have a list of unspent outputs. On Ethereum, you have similar things, but they are called a little bit different. You have transaction parameters that go into the transaction, and a smart contract can and should, that's what the standards define, they should produce log entries. So basically some output entries that define the state change or describe the change of the state that has happened in the transaction. Yeah. Those two things are important, for example, to index and to understand what ERC20 tokens do, what mints do, what transfers do. In Tezos, you have the same. You have transaction parameters that you send into a transaction and to a smart contract. But instead of transaction receipts, like explicit log entries, Tezos only gives you a diff of the storage changes. Yeah, that sounds different and sounds difficult. And we go into the different indexing strategies going forward. So instead of receipts for kind of what the contract did, how the state changed, from the perspective of the contract, you actually get a state change of the perspective of the storage. So that leads these different kind of ways how blockchains kind of manage these state changes and kind of export information about these state changes, leads to three different indexing strategies. First strategy, this is the one you would do for Bitcoin, is you do it parameter-based. Parameter-based basically says you predict the state change, the outcome of the state change, based on the input parameters. You only have to observe the input parameters, and because you know what these input parameters will do, because you assume there cannot be any other outcome, because you know that kind of on Bitcoin, the script or the possible spending situations are very confined to a certain set of kind of scripts. You can basically predict based on the input parameters what the outcome will be. Yeah? This works for layer 1 Bitcoin. This works pretty well for some of the layer 2 solutions on Bitcoin, like OmniLayer. This just kind of works. Yeah. Also because these standards are made in a way that it works. This starts failing, this approach, only looking at the inputs, when you have things that are concealed, that you don't really see, that you don't have enough information about. For example, when you have complex scripts on Bitcoin, yeah? Everything that's behind a script hash, starting with 3, and addresses starting with 3. Those are script hashes, you basically don't know what's behind the script. Yeah? And you only know what actually happened and which addresses were really involved in a transaction when somebody publishes the spending script and spends the coins again. But as long as they are unspent, you don't know anything. And your only fallback solution is, you just use the script hash and you just attach the Bitcoins on these outputs to the script hash and keep it hanging around until you know how the script really looks. And then you can reattach it to the original kind of addresses that are mentioned in the script. So that's the limit of this way of indexing. So it only works with Bitcoin and it only works in a few situations nowadays. The second strategy is receipts-based. So what you do is you track the outcome of such an operation that happens on-chain based on the reported state updates. So basically you assume that the smart contracts output log entries. This is kind of works for Ethereum. and you assume that these log entries are correct and complete also. So these smart contracts don't hide anything internally. And this works pretty well if the implementers of these smart contracts are kind of trustworthy and they did a good job and they really export everything. But if they don't export anything, do something fishy, this breaks. There are some ERC20 contracts on Ethereum that actually do fishy, strange things behind the scenes where it's not really exported. So there you have to dig further and you have to understand what's going on in these types of contracts to do a proper indexing instead. Tezos layer 1, like the normal Tezos, they work pretty well. So everything that the blockchain, the Tezos blockchain RPC exports to you, all the balance updates, for example, you can trust them. And you can do indexing based on these balance updates. But as soon as this RPC response contains some incomplete data, you are basically screwed. In Tezos, there are still some bugs in the RPC layer, and there are some situations where you can't really trust the outcome. Not for balances are totally okay, but there is, for example, the state of bakers, whether they are active or inactive. There is a bug which doesn't really signal when a baker becomes inactive again. So you'd have to do a different way of kind of indexing in this case. The third strategy, and this is the strategy we have to do for Tezos smart contract indexing, is storage-based indexing. So what that does is basically you observe the updates to the storage in order to detect what has happened during the execution of the contract, and you adapt your own index, your own database model to what you actually saw from the outcome. This is kind of an indirect indexing strategy. And the problem with this is it's quite fragile, because usually when you build a software, what you do, or when you build a function, you only specify its interface. And when you do a standard, you only specify the interface standard, like the calling convention, the input parameters. And Tezos, there's no output parameters, so you only specify the inputs and maybe the function names. But you leave out of the specification all the internals of a function. Yeah, it's kind of the modularity principle in object-oriented programming. You shouldn't be concerned from the outside, you shouldn't be concerned with what a function does internally, as long as it kind of fulfills its interface specification. For indexing Tezos smart contracts, this breaks, because we only see storage updates, but the storage updates are maybe 2 or 3 layers underneath the interface definition. So what we have to do in order to index Tezos smart contracts is we have to understand how the storage layout looks, and we have to understand what changes to the storage or to storage entries mean in order to basically track what's going on. And this is a current limitation to what we can do with Tezos. Like, everybody can build a crazy contract that does a lot of things and does changes to the storage, and you are basically free to not document what's going on in storage. You are free to not annotate your smart contracts. But if you don't do this, you will have a hard time, or other people will have a hard time indexing your smart contracts. So you can kind of hide information there, but you yourself will have a hard time understanding what's going on. And as soon as you do a change, and your storage layout changes, you also have to change your indexing strategy. So that's not an ideal solution. And I have some ideas what to do, maybe. But yeah, be aware. So in Tezos, annotations are optional, basically. You don't have to do annotations, but if you do annotations, indexing gets better. In Tezos, you can work with binary data in your contracts. So you can kind of put data on the stack, you can pack the data, that becomes a binary blob, it's stored in storage somehow. Many people do this, and we go into details how it looks when you kind of try to make any sense out of it. I mean, in Tezos, you can unpack it in your smart contract, and then you can work with it, because you basically know what each byte means and each bit means. But it's only you as a contract developer who knows that. Me as an index developer probably doesn't know it, and probably I can't build a good index for you. But maybe I can give you tools so you can build a better index for your own code. Yeah, and there's certain limitations in Tezos. Like for example, pack doesn't support annotations. It still supports types, so you can still pack types because Tezos storage is strongly typed. Like every piece of information is typed unless you do really make a byte slice and just throw in some arbitrary bytes there. You'd still have typing, but the type support is basically limited. So you wouldn't understand whether kind of a byte blob is an address or is a signature or something like that. Or you don't understand if an integer is a real integer or it's a Tezos amount or it's a timestamp. So those are the things that get lost in pack, between pack and unpack. And kind of one of the things we are trying to discuss right now with people who build kind of these standards on top of Tezos is, right now standards are only concerned with the interface, which they should be, basically. Yeah, that's the kind of the good thing what a standard should do. But since there is also the need to index data around smart contracts and index data around this FA 1.2, like this ERC20 equivalent on Tezos, there is a certain desire to also kind of have a standardized way for indexing, so everybody could understand this. And but we are not there yet. All right, so that kind of concludes kind of the deep dive. Are there any questions?
So, regarding the last part of what you're saying, that from the indexer perspective, basically you need to trust an interface that gives you a specification of the contract. What would be, from your perspective, the specification for the Tezos smart contract there? What would make your life happy or easier?
Two options. One option would be to introduce receipts. So smart contracts could write receipts, like state updates. Supply changed that way. A transaction happened and now funds have moved from here to there. This could be one option. The second option, if there was no receipts, the standards should also standardize storage. Not everything, but only things that are relevant for being exposed to the outside world. The third option would be to build tools that basically look a little bit similar to what the graph does on Ethereum, where kind of the indexing developers, like me, give you tools and you kind of build along your contract, you build another function that aids the indexing of the contract storage. And every time you change your contract and you know you change the storage layout, you also change maybe a description or maybe some code. And then you inject this new code into the indexer. This could also work. So that's basically three types of options. And we haven't even started discussing what would be a good strategy going forward. Maybe the first because it's the least invasive, but it probably also takes the longest time to develop and get it right. But yeah, it's basically up to us that we develop tooling for Tezos, and also kind of maybe talking to everybody at Nomadic. All right, then I would jump into this, and after this is just like 4 or 5 slides. We have a short break. Yeah, this is cool? Good. Yeah. Okay, so there's a couple of different indexers available, different implementations, and this is good. I mean, Tezos only has 2 core development labs, which is also okay, but it's even better to have way more tooling companies sitting on top, because if one of the guys or one of the companies screws up or even goes away, the others will survive. So there is options to pick, and there is kind of a healthy ecosystem, and you don't rely on one single entity and the bugs that come out of this one single entity. So there's different indexing solutions for Tezos, And I'm briefly going over these different solutions. When you click in the PDF on the picture, you actually, this is a link to the repository where you find these indexes. So first indexer, because we are invited by NomadicLabs, thank you so much for having us. So the first indexer actually comes out of the core developer lab. It's the NomadicLabs indexer, or the lib indexer, as it's called. It's a tool implemented in OCaml, and basically follows from its architecture, it follows the Tezos protocol implementation. So for every different protocol that gets activated on Tezos, it has a specific implementation, and it basically indexes the data from Tezos based on the protocol. And it uses kind of the same data structures, which is nice. So you have kind of a link between the node implementation and the indexer implementation. But what you have to know about this is that it's just an ETL job, basically. It's a very thin layer, just a very thin, very small extraction program that just does the extraction, the transforming, and the loading. And what it basically does, it extracts the data from the RPC, I think, and puts it into a SQL database. It requires a Postgres database server and just puts it into the database. It also doesn't extract everything that is possible to extract. It basically looks at the balances and I think the delegations, and it only indexes some of the operations that exist, not everything. It's also a work in progress, so it kind of grows, but it's also kind of a tremendous job to do this. I know it myself because I implemented this other indexer, and it takes a long time to really build kind of a fully fledged indexer. So what you get here is you basically get a tool that fills a Postgres database for you. And after that, you are on your own. So you can build whatever tooling around it, but you also have to. So there is no API. You have to build your own queries. You have to also configure the database, get the right indexes in place, and so on. So that's kind of the first indexing tool in the landscape. The second tool, done by Cryptonomic, it's called Conceal. It's written in Scala. This is kind of a full-fledged blockchain indexer and API server, so it contains both things. So it indexes the blockchain, but also has an API where you can crawl the index or can get data out of the index again. Under the hood, it also uses Postgres as a SQL database server, and it uses kind of a large amount of indexes to just be fast. So it finds the addresses, it finds transactions to addresses, and so on. It has a quite verbose language, like query language, that maps to SQL queries internally. And this query language might be maybe a little bit tedious, but it's also highly expressive in a sense. So if you really, really want to or need crazy filters, much expressiveness in your queries, Conceal might be the right solution. But still you need a separate database server, Postgres server, you need to manage that, and you need this Conceal server. It's not really made for statistics. It has some kind of balance history statistic, but that's basically it. A nice thing about Conceal is, because when it comes to smart contracts and also storage, it stores the raw JSON output that comes from the node. So every storage update, all the parameters and so on, it basically stores these primitive trees in the database. And what it gives you is you can do a full text search over this. So this is one of the very few solutions that actually allow you to do a full text search. For example, when you want to search who uses this opcode and which contracts use this specific opcode, you will find this with this solution. None of the others can find it for you. Then there is a new indexer from Breaking Bad. This is a software they did for their new block explorer. They implemented it in .NET, so you need the Microsoft toolchain to compile it and to run it. Of course, it also runs on Linux because .NET is also available on Linux these days. And it basically splits into two components. It does, the one component does this extract data from RPC, transforming it and loading it into a database. And the other component is the API server. The idea behind this is that you only need one extractor that extracts from a node and fills the database, and then you can maybe replicate your database, you can have more database servers that are kind of synchronized with each other, and you can have different front ends on top, so you can scale out horizontally to more load. So that's the idea behind kind of splitting these two things from each other. The nice thing is they support a little bit more information, so they also pull data that is sitting in the mempool, which is not confirmed in blocks yet. That's a nice feature because there you get a little bit more insight into the future of the blockchain, what's going on, and a little bit faster reaction time to what's actually happening around your calls or your transfers you send. So that's a nice thing. But it also requires a separate Postgres server. And as I said in the beginning, Postgres is nice when you want to build fast and when you want to do kind of flexible queries. But as the blockchain grows, your operational costs grow tremendously. So right now there's not so much happening on Tezos, but when we assume that Tezos becomes kind of the new Ethereum or the new Bitcoin of smart contract platforms or whatever, there will be much more happening on Tezos going forward. And these databases that are maintained by the indexers, they will grow tremendously. You know? So we need to be prepared for this. And such types of solutions that use SQL databases are good for the next maybe 3 to 5 years. But after that, the operational costs are so high that only very few entities might be willing to pay the operation costs for that. So this is something we should consider going forward. But as smart contract developers, this is not your major concern. This is more the infrastructure operator concern. They don't support smart contract data yet, but since they also build Baking Bad, or better called Dev, this is features that will come into this indexer solution as well. So, and the last indexer in this list is the indexer I built. The idea behind this indexer is to have low operational costs and fastest possible speed of not only indexing, because indexing you don't do so often, but the queries should also be extremely fast, and it should lend itself to analytical queries. So you can kind of grab 50,000 transactions in one call, or you can aggregate over 1 year of data in a couple of milliseconds. So that's the idea behind this type of indexer. As I said, it builds on its own database engine. And the nice thing from an operational perspective is that the database is actually embedded. You don't need an extra database server to run this indexer. It's just one binary you just fire up, and it syncs against the node, and it contains the API and the database. So it's a very lean solution, and it's a nice solution because it doesn't need so many resources. You can run it on a laptop. You can even crawl mainnet on a laptop and be happy and do all your other work on a laptop. So you don't really need so much resources to run this. Because I know I want to index smart contracts fully, especially because of these token contracts and so on. I don't want to store raw JSON data as anybody else does. I want to actually only store binary data. I need to implement the binary decoding and re-encoding. So this is also something that comes with this indexer. It has kind of a full support for this Michelson JSON to binary to JSON, whatever, in all directions, encoding, decoding. On top, it has some interesting APIs. It has a time series API where we get time series data. It has a table API where you can basically look into the raw tables, like all transactions or all the different flows that happened or all writes. Basically, like everything that happens on Tezos, it's in these databases as a table. It doesn't have mempool support yet. Maybe this will be a separate tooling coming out this year, and also doesn't have full text search. So all these different indexing solutions, they are all open source. That's what the Tezos Foundation kindly requests from everybody who gets kind of funding from them, which is a good thing because then everybody can use these things and build basically new tooling on top. Let's have a break here before we jump into the gory details of APIs. The next part of this presentation or workshop, it is actually, now it's starting to be a real workshop. You can click if you like, and you can also try and play around with a lot of things. I put quite a lot of links into the PDF, so if you have the PDF open, you can have it open in one window and a web browser in the other window, just to follow what we are using most of the time is kind of the new version of the TC-Stats API. This one is not live yet. It's on a staging server on our end, but also our BabylonNet and CarthageNet backends are already updated. It's just that mainnet is not the updated version, and that's why the current documentation you'll find under this link, under the staging tcstats.com API description. So that's basically all the API description. You don't have to go through this. If you want to read about more details, please feel free to have a look. But what we are going to do is we are going to kind of look into, oh wait, I shouldn't touch it. Oh my God.
Okay.
Oh no, here we go again. So we are going to have a look at what an indexer API can do for you when you implement smart contracts, and especially when you implement tooling around your smart contracts. So when you want to understand what's going on inside your contracts, but also when you implement, say, a website or another system that works with data in your smart contracts. Bear in mind that this indexing solution or an indexer is only a read-only tool. Yeah, so there is no way to interact with your smart contract directly. Yeah, this is done through other tools. Here, you get a read-only view into what your contract does or did in the past. Yeah, so just to set the stage. So there are some interesting contracts I pulled out of the different networks for you to have a look. And it's kind of totally different things. There is a DEX. This is the one done by Baking Bad. There is this Staker DAO, which launched in January and doesn't have so many transactions yet, but it might be interesting to have a look at it. Then there is a very early contract, these Tezos Foundation vesting contracts, where kind of some millions of their coins are still kind of locked or kind of slowly getting unlocked over time in the net, and kind of where they could actually start moving funds, but they don't do it. And then there is this Baker registry contract, where bakers can register certain information about their operations, about their addresses and so on. Those contracts, they all live on mainnet, and then we have some contracts on BabylonNet that are maybe interesting. There is this one contract that implements this FA 1.2 interface. Then we have another contract, DS token. That's the thing that's used by Securitize or Elevated Returns to do their real estate tokenization project. And then we have another contract that's relatively kind of new and unknown, which is kind of wrapped Bitcoin. And these contracts down here, like DS token and DCBTC, so DS token is pretty old from a kind of technology perspective. That comes out of a time when there was no big maps, so it only uses the regular storage information. There's other contracts who use big maps extensively, and that's this Baker registry, FA 1.2, TCBTC, and so on. So I just want you to know that these contracts exist and you can use them. And the idea behind kind of this workshop style thing is when you kind of click on one of these contracts, the link opens on our API. So this is the API response you get here. So, and just to jump into the responses right away, so what you can get. First couple of topics is inspecting your contract. So just understanding what it is, what's going on around your specific contract. So the first call to the API /explorer/contract and then the address gives you some high-level information, some high-level metadata about your contract. You see address, you see who's the manager. If the contract is delegated somewhere, you see also the delegate. You see the height, so the block at which the contract was originated. You see the fee, the origination fee and the gas costs and so on at time of origination. You have some flags. Is funded usually says if there are coins sitting on the contract or not. And then some special other flags for delegations and so on. And then this first in, first out, last in, last out, first seen, last seen, they are both in block heights or levels as they're called in Tezos and in timestamps. They basically give you an overview about what and or when was the last action happening around the contract. Yeah, this in and out refer to transfers that transfer tokens to the contract, and when you only have calls, then then this last scene gets updated. And the other things, that you have some counters, so the number of operations that were sent to the contract, maybe the number of operations that failed, and so on. Then also transactions in general, could be other operations that are sent by the contract, like delegations, originations, and so on. And one field that might be the most important is the which bitmaps the contract actually uses. So that's basically the first call, just to give you a little bit metadata. So what's actually really interesting to us is, okay, what's the contract doing? And that's this script endpoint. And in this case, we have, this is the Baker registry contract. And just to give you the high-level overview, this endpoint gives you two types of information. It gives you an understanding about how the storage is structured inside the contract, and it gives you a list of entry points you can call on the contract. So let's look into the storage. So here, the storage defines that this contract is using a bitmap, and bitmaps work in a way that you always have a key and a value type, key type and value type. And so the bitmap item contains like these two entries. The first is the key type and the second is the value type. In this case, we have a bitmap where the keys are key hashes, meaning addresses, and the value is some sort of a complex structure. And what you see here is already kind of a decomposed, or we call it unboxed representation of this contract storage. Because originally, this contract storage, when you get it from the RPC, looks like this. When you add the prim equals 1 or prim equals true to get the primitive tree also, this is what you basically see when you call the Tezos node. So you see, oh wait, this is the code. This is the storage contents. So this is basically the structure, like a nested tree of JSON objects, which specifically defines how the contract storage looks like, or also how the parameters look like. This is the first argument. And this complex data, in this case, is dissected by the indexer and represented in an easier to digest way. Yeah, on the storage type, you find a structure that looks, which is kind of also nested JSON objects if the data is nested. And in each nesting level, you see kind of an order number for each item, which defines, okay, at which point, at which order number this data item was defined, and then an @ symbol, and then a name, and this name is something you have given in an annotation to the specific type item in the storage description. Yeah? So that's the annotation name, and after this you see the type that is specified in your contract. So when you write a contract, you specify out the storage type tree, and when you have a chance to put annotations, please do, because then this API or this indexer can extract these annotations and give you more human readable experience. So that's the storage type, so this is just like in general the typing you see inside your contract. And then you have the entry points, and this contract only has 3 entry points. It has a set data entry point, and this set data entry point has a type, and the type is basically the function type that you call here. Yeah? And it says, okay, the first argument is called delegate, so it has the annotation delegate, and it's of type key hash. The second is an optional type. It's called data, and it's kind of a more complex structure. And the third argument is the annotation reporter account, and it's also optional, and that's an address. So you can look in here, and this data kind of then contains other fields which are of different other types. So that's the type, and what we add to these entry points is kind of an order number. We call it ID here. So the first entry point is 0, the second entry point is 1, and so on. And we also add the branch in the code how this entry point is reached. So because these entry points are structured in OR pairs in Michelson. So in these OR pairs you either go left or right, and then you have this path going through your tree of pairs, and when you follow left, right, you always end up at kind of these specific entry points. And what this indexer detects internally is, okay, where's the path? In this case, it's very simple. It's only kind of the first left branch and the first right branch, but there is more complex contracts where this can get very deep. And so you basically know, based on this, it's very short, concise expression which branch you're basically calling. This is just like a convenience parameter, so to say. And originally, what you basically get from the node is kind of this primitive tree, where you see here, this is the name, this is the annotation, and then you see the arguments, these pair arguments. So this is what you usually get, but from an indexer API, you get actually this kind of a more decomposed version. So that's kind of the script information, so how storage looks and what entry points exist. And next thing you might be interested in, okay, let's look at the calls that this contract received. So, and these calls, they are structured in operations, so we have a lot of metadata about all these different kind of things that go around an operation, like which block height, which cycle they were, how to find them on the blockchain, and so on, how much gas costs were paid. But what we are interested here right now is actually only the parameters that are kind of the input parameters to the function call. And here we see, okay, this is the original entry point that got called in the transaction. Oftentimes you only see a default entry point there, which doesn't really tell you much, because then you really have to dissect the path of these argument parameters down. And in our case, we see that the branch or the path that was called was on the left part, which in the end was the set data entry point that got called. And this is the entry point with ID 0. And this is the actual data that got sent into the call. So the set data function on this smart contract was called with the data argument, and this data argument basically contains these different fields. And on the left-hand side, you see the argument name that you find in the annotation, and that matches to the type annotation we just saw. And on the right-hand side, you see the values of these elements. Yeah? And actually, the original call parameters only contain the values. They don't contain all these names here. This is just the convenience, what the indexer does for you and what the unboxing mechanism does. It just gives you kind of a nice JSON object where you can really see, okay, and understand, yeah, open for delegation was actually true in this specific case. And these renderings on the right side, they are already kind of typed, meaning this was actually a binary block in the original call parameters, but what the indexer does for you is it really gives you an address, because it knows that this field here, delegate, is of type address. So it can actually render the address as a real address for you. And that's kind of the nice, convenient way of doing this. This call also updates two things. In this case, it updates the storage of the contract. So this is kind of a return argument. This is what I said about Tezos, that we get a receipt from each transaction, and the receipt contains nothing the contract specifically created, but something that was implicitly created by the contract, namely the storage changes. And since Tezos knows these two different types of storage, kind of this regular storage, which is kind of a full blob of data that is owned by a contract, which is called storage, and then it has these big maps where you have this key value store. You basically find in different operations that are sent to contracts those two things. Some contracts don't have storage, some contracts don't have big map, then one of these is missing. But some have both. So in this case, we have both. And basically what we see is here we have a storage. Storage is always structured in kind of a meta information, metadata, and a value. And this is the value, the type for this we just saw in the script section. Here we have the owner sign-up fee. So this is kind of the smallest static storage. And here we have a reference to the big map, number 17, and the big map diff reference is also the same big map. And the big map update, we have down here in the call. I go into detail about big map updates later, but basically you see kind of that this key, this address, has a new content now, and the new content is inside this value, and that's kind of all this compact data argument here, which is kind of a structure of different values. So these calls on the API, you can list an indefinite amount of calls, but for each API request, you can at most request 100 different calls. Because these data items, they can grow large, and we just don't want to kind of overload you with so much data, and also don't overload our backend systems with so much data, and be kind of nice to other people who use the API. So that's why there's some sort of a limit, and the limit right now is you get, with one call, you get one call to the API, you get 100 smart contract operations out of the API. So that's why you can set a limit to 100, to at most 100, and in order, if there is more calls, and you see this from the metadata of the contract, if there is more calls that happened and you want to see all of them, you can then set the offset argument, and with this you can page through the results of this endpoint. Yeah, so that's pretty simple. Let's do the next part. So we already saw in storage update, and when we go to, I don't know if this is the same contract. No, it's a different one. So in this case, this is a contract from the Tezos Foundation, which is a vesting contract where kind of coins are locked that are owned by the foundation and can be paid out after certain amounts of time. And when you look into the storage, so this is kind of a very old school contract that has been published in the Genesis blog. of the Tezos network. So it kind of uses the very first features of smart contracts in Tezos, no bitmap, and so on. And the storage endpoint gives you a view into the current state of that contract. So as of the tip of the blockchain right now. We will later on see how you can get a past state of the contract storage also. All right, now this is the most recent state. It gives you some metadata about the current state. You actually see that the last update to this specific contract state happened at block 30, sometimes in 2018, and you also get the block hash where the update happened, and the value basically defines a decomposed list of information that is stored in this contract right now. So you see in this case some key info, so a lot of signatories, so keys that need to sign operations to move funds out of this contract. And then you see kind of these vesting settings that are going on in this contract, and you see kind of the how often kind of this contract is allowed to vest, and how often it pays. So it basically pays once a month. But since it hasn't been used, they are actually allowed to vest much more of their coins right now, but they just don't do it yet. To just not kind of stir up a lot of speculation about why they are doing this. So they just keep their coins being locked, although they could actually move the coins out. Yeah, as I said, you can dissect storage, or you can get the raw Michelson information. If you have to have in a parser for these Michelson type trees, all these nested pair and arc trees, you can always get the raw data information out when you set prim to true. And you also, and this will become important later, you can also request the API to unpack packed data. So there are some contracts who use this pack instruction in Michelson to pack binary data in a binary block. And this data is usually typed, and we can make sense out of it when we unpack it. And in order to do this, you can instruct the API on every call that exists around smart contracts on this API to try unpacking every field that looks as if it was packed. And then it tries, and if it's successful, then you get an unpacked value as well. Let's jump into the bitmap API, and let's have a look at the bitmap. So first of all, there is some high-level information about bitmaps available on the API. So there is the owner of the bitmap. So in Tezos, a bitmap is kind of this key value store that is owned by exactly one contract. But one contract can own multiple bitmaps. You can also copy bitmaps and create new ones on the fly. You can also kind of remove old ones, then they vanish from storage. So for the bitmap, you always understand which contract owns it, and you understand how many updates have happened over the lifetime of this bitmap, and also how many keys are stored in the bitmap right now. Then you get some information about the allocation time and also the update time. When you want to look at the type of the bitmap, so we saw the type of the bitmap already in the storage, in the contract script information. There it was also contained, but just for convenience purposes, there is also a type endpoint, and that's kind of the same thing. It's the Baker registry contract, which gives you only the type information of the bitmap. So you have this key type, and you have the value type. When you want to read a single entry in this bitmap, you usually have a key. When you do this via the JSON RPC on the node, you have to have this expression hash. I don't know who of you have already kind of worked with this bitmap, but this expression hash is something that starts with EXPR, and then it's just a hash afterwards. And that's quite tedious to get, because most of the time, I mean, in my bitmap, I store addresses, and I store some information for addresses. So what I have right now is I know the address, and I just want to use the address as a key, and not create the expression hash out of this. And this is the beauty of an indexer. You can actually use different kind of representations of a key to access the data behind it. So you could use the expression hash if you have it available. If you don't, you can also use the native value, whether it's a timestamp or whether it's an address. You can just use this. In this case, this bitmap happens to use addresses as keys, and we will find the corresponding data item to this key under the address. Yeah? So that's the basic key. You also get, as a convenience, you get the expression hash, so that would also lead you to the same entry, and you also get the binary representation of that key. This is kind of the binary representation out of Michelson. And then you get the value. Yeah? This is basically the same what we saw in the listing. Plus on top you get some metadata. You understand when this entry in the bitmap was created and whether it has been replaced or updated subsequently. So right now, because we don't do any extra parameters, this is the most recent version of that entry in the bitmap. But you can also, this is what we'll see on the next slide, go back in time and look at the version of that bitmap entry sometime in the past. Another feature, and this is something that doesn't exist on the RPC, is that you are able to list all keys that are in the bitmap. I mean, I guess it's easy to add it to the RPC, and probably this will happen sometime in the future. But right now it doesn't exist, and there is the need to kind of list how many keys or which keys are actually contained, or also list the values in the bitmap. And there is just this convenient method to list all keys. And the same thing for listing. Oops, sorry. Okay, bad URL. I'll fix it. List all values. No, gonna fix it later. Okay, so I was talking about this historic access to block information, to bitmap information. So sometimes it's important to understand what happened in the history of your smart contract. You have some calls coming in. These calls update bitmap items, maybe they override things, maybe one item is overwritten kind of often, and you need to understand, okay, when it was overwritten and when it was at a certain state. Now, for example, let's look at contracts, for example, that store this FA 1.2 or that implement FA 1.2. There you have a field that says whether the contract was paused or not. So the administrator of this token can pause transactions on a contract, and by just sending a pause function to the contract that updates the state to paused, and then the administrator can send an unpause, which kind of then allows more transactions coming into the contract from other people. And you want to maybe understand kind of history of pause and unpause events. You know? And for this specific case, you maybe want to understand, okay, was the contract paused on January 1st, 2020? And in order to do that, you can append another parameter to the API. And this can happen to all the different endpoints, so for listing keys or for listing values, but also for a single key access. You basically add a block hash or block height as a parameter, and the index will look up the state of this bitmap item at this point in time, at this block. Yeah? No matter if it has updated before or after or exactly at this block. So it just give a block and it will look it up. Now, Tezos has no finality, meaning the blockchain can reorganize, or it has actually an extended finality, like 64 blocks. So there is a window in time when the blockchain can reorganize, when there is a longer or more heavier chain or a chain with more endorsements, to name it in Tezos terms, available. So when you are looking at your bitmap items and they are very fresh, so they are coming out of the last minutes, and you are a little bit unsure if this state will remain kind of the final state for eternity, it makes sense to add the block hash, even current block hash to it, while you look at these items, or when you kind of list entries out of a big map, and you just want to lock the timing of your listing to a specific block, you should add a block hash to it, which kind of locks the call at this point in time and gives you the viewpoint of this point in time. Now, when there is a chain reorganization happening, and this block becomes an orphan block, like on a side chain, and the true chain, the true state, is something else, and you do another call, you will get an error out of the API. Yeah? This is a very important concept, because when you have a reorganization, you can't really be sure, as long as you are looking at the most recent blocks, that this state is really final. Yeah? And in this case, you get a 409 conflict HTTP error out of the API if there was a reorganization. So you don't really have to check and have to have a complex logic around to really track chain reorganizations and so on, because that's what gets you, what you get out of the API. So in this case, I suggest to use the block hash instead of the hide, because the hide is basically the same across reorganized or different side chains, but in this case, the block hash is kind of very specific. When you want to monitor for updates, so right now, this API doesn't have a notification mechanism built in. That will happen sometime this year, but right now it's not there. So your only way to basically understand if there is something new happening around your smart contract is by knowing the last state you checked at, and you just keep the block hash around of that last state, or maybe the height. Well, block hash, as I said, is better because of reorganizations. And then, when you do a next call, you can basically use this last hash as a since parameter to these endpoints. No matter if you list for operations that are happening on your contracts or for updates on big maps, they all support the since parameter. And this basically filters out all the information or all the new updates that happened after the last time you've seen an update. Yeah? So you don't have to parse out all the recent updates or everything. You can just kind of continue to crawl, and the next time you call with this parameter, you don't see an update, you know nothing happened. And as soon as you see an update, you keep the new block hash around and put this into the next call. So you can hop by hop by hop kind of get your updates for the API. All right, so that was kind of a quick overview of the APIs that are available for smart contract developers on Tezos. I think tomorrow, when we do this hacking session, we go much more into detail. We look at your contracts you deployed, and we look at how they look from a type perspective, how their big maps look, and so on. So you get a closer touch to what could be done and how you could structure applications around smart contracts. Those are the last two slides, and then my part of the talk is over. The remaining thing right now is to give you an idea what you could do in order to build smart contracts on Tezos that are easier to index, or said the other way around, what you should avoid, which makes it harder. So the things you should consider when you build smart contracts. Always use annotations. Annotations make it possible for this unboxing to work and to give you kind of JSON objects and hierarchies of JSON objects that make sense to you, because you wrote the name of the variable as an annotation, and the exact same name will appear on that API. If you don't do that, you will just get a generic created name out of the API, which also works because you know the order, and the order is yours as you implemented it, but it may be not as convenient to other users of your smart contract. So consider doing this, and also consider naming your entry points, because if you don't do it, you also get a generic name for entry points. This is more generic thing, the last part. When you have when you store data that you know will grow in size over time. With more users using your contract, always use a big map for that. Because when you use the old school storage, this storage is always put in its full into the receipts of a transaction. So that just blows up the amount of data that you will have to digest when you look at your contract calls. Yeah. Say, for example, you want to store a megabyte or more, or 10 megabytes of data. You should not do this in the regular storage. Because with every single transaction that goes on, this will be kind of output as a result in the transaction receipt. That's not good. So things to avoid. So pack and unpack might be convenient, but right now they don't carry along all the type definitions that make Tezos so useful. And especially they don't carry along the annotations. So every time you use pack, you lose all that convenience. And also on the API of an indexer, in this specific case, you lose the convenience of having named variables. There is a lot of examples in these contracts, like TCP/TC, for example. They use pack for big map keys, and they use pack for big map values. And both look tremendously ugly and don't tell you anything. When you use the special unpack feature of this API, it gets a little bit nicer, but still you don't have names. You only have types and kind of sequence numbers. Maybe not ideal. But I mean, if you have to use pack, okay, do it. I can't hold you back from doing this. But maybe to the implementers of the Michelson language, I don't know if anybody of you is kind of involved with kind of the Michelson part of it. Please figure out a way to put type annotations and a full typing system into the pack and unpack. Generally, you could also kind of build on the stack, you could build kind of binary blobs and store the data just as binary. There is contracts like the securitized contract, they do it. And you won't understand anything about their keys in maps they are using, because it's just some sort of binary blob. That's maybe good for you because it's easy to implement or because it's intellectually challenging, but it's definitely not good for your users. So try to avoid that. In Cartage, there is this new feature where you are allowed to have pairs and also kind of trees of pairs as keys into big maps. That's an interesting feature, and I know functional programming people love it. And there's lots of use cases for this. But please, if there is a way to avoid this, think about your downstream users. It's not so much the indexing developers. I did it now. It took a couple of days to also implement pairs as big map keys. It's fine. The API supports it now. But please think about your users who have to kind of understand the data that comes out of your contract and kind of build an application on top. This makes it much, much harder to build an application. Try to have simple keys. And the last thing, there is a couple of contracts who went a little bit overboard with kind of annotations, so you can also do too much, especially when you do too many annotations on the parameter trees that define the entry points. When you name every OR branch in that case, tooling gets confused what the real name of the entry point is. Yeah, and when you look at for example, the contract we just had, this vesting contract from the foundation, this is one example where they have kind of a top-level action name attached, or action annotation attached to kind of a high-level OR, which kind of messes up our finding of the real entry points of that contract. So it's just for your own sake and for the sake of your users to not do too many annotations for especially entry points. For types, all is good. For types, you should annotate everything, like every single little detail. but for entry points not. All right, so if you wanted to run your own version of this indexer that comes out of us, this is what you would basically do. This is one kind of Go program. So if you want to compile it from source, you'd have to install Golang on your machine. If not, you could use the Docker container. If you don't want to use Docker, you can maybe ask me and I give you a binary for your system, whatever. The idea of running it is pretty simple. It's just the name is index and then just a run command, and after this you give a flag, and the most important flag is basically this RPC URL down here, which just takes a string that connects to your blockchain node. And that's basically it, and then it should run. So it kind of runs with all the different networks. Right now in this open source version, Carthage support is not updated yet. It will come in the next 2 weeks. And it also runs against sandbox networks, so you can run it at home. You can also run it against kind of public endpoints. There's a lot of people who kind of provide RPC access to nodes kind of freely, openly on the network. It doesn't use so many different RPC endpoints, especially not the ones that are kind of blocked. So basically you could use almost every kind of free and openly available kind of RPC nodes. You don't have to run your own node to run this indexer. And then you get all these different features of the API, plus kind of a lot more around every aspect of Tezos. Thanks so much for your time. If there are questions right now, I would answer them now, otherwise in the break, afterwards, or tomorrow. Yep.
Does the enable course flag replace the unavailable that we have to put?
Yeah.
Okay.
So some people asked about cores, because when you also run kind of a website against this indexer, it's how basically web browsers work when they call APIs. They need this cross-origin resource request security feature, and when you set enable cores, this is kind of convenience flag.
Because before we had to put in
Yeah.
unavailable.
Before you had to set an environment variable, or you can also specify this in the configuration file. And the default setting was it's off, and those are then 3 ways to kind of enable this. And so, yeah, that's the convenient way now, because somebody asked. All right, thanks for your time.